So we've only got one more thing to do in terms of generating new rules and new ideas, and that's to look at what does a bending moment diagram do when you've got a line load. Now, what I'll do again is I'll just work through the method of sections. I will not make you sit through it, but one thing you'll notice, just remember this one. So I found the reactions. To find those reactions, I would have found an equivalent UDL at the center. Actually, it's symmetrical. The load's constant. We just decided, well, it's going to be the magnitude of that load is just the area under, so 12 times 6, and it must be shared equally because it's a symmetrical loading. So we didn't even calculate anything for that. But what we do have to remember is when we start doing the method of sections, then it's the case that you need to put that UDL back. You can't just keep if you've changed this to a point load to get those reactions at each side, you can't use that for the method of sections. You have to change that back to a UDL and find out what the equivalent point load is for that little section. Okay, so I'm not going to make you sit through me doing all these calcs, but what I'll do next is I'm just going to run through all this. I'm going to get rid of the shear calcs, and then I will just do all the calculations for the moments, and we'll come back and have a look at it after I've done that. Okay, so I've managed to get through all that. So what I've done is just the method of sections to figure out the moment at the end, just moving along the beam, 1 meter, 2 meter, 3 meter, 4 meter. Could have kept going, but one thing we can see is this is going to be symmetrical, and so the beam's loaded symmetrically, and so the moment diagram must also be symmetrical for this one. And so I haven't bothered doing M5 and so on. What I have added though is just one right next to the support. And if you work through, so you just imagine you just come a tiny distance, M0 plus, and if you just go through the calcs for that, you'll see that the moment must be 0. And that makes sense because these supports, that's a pin, that's a rocker, they only have X and Y components. They can't have a moment, so there can't be any moment at the end of this beam. So this moment diagram must start from 0, and you use that quite a lot. If there's a pin at the ends of a beam, and in fact, if there's a pin in the middle of a beam, you might get that in some situations. I'm not really going to do it in this course, but you also know the moment is 0 at that point. So if we now plot these, so because it's got pins at the end, we know that that must be, I'll just do it, and I'll do it in blue actually. You know, that must be 0 and this must be 0, okay, at 0 and 6 meters. Then we've got some of our results. So at 1 meter, it's going to be 5 kilonewtons. 3 meter, oh sorry, I did do 2 meters. 2 meters, it's going to be 8 kilonewton meters. Sorry, 8 kilonewton meters. At 3 meters, it's 9 kilonewton meters. So it's about there. And then it's symmetrical. And so we can go back down symmetrically rather than calculating it all. So if we were to figure out all the other points in between, what we'd find is we would get a curved line like this. And for those of you that remember your maths, it's a parabola. And so that will have a formula like, you don't need to know this because you can do it without it, what we're going to do, but it's going to have a formula like y equals something times x squared plus something times x plus something. And it's not y, it's m. And m, remember, positive is down the way. So all these are positive, so they're all down the way. It's all sagging, which makes sense. This beam is going to sag because it's got that load on top of it. The deformed shape is going to be like that. And the curvature at the end, this will be pretty low, curvature in the middle is high, and that's what we're getting. So moments related to the curvature, it's going to be no curvature at the end, very high curvature in the center, and no curvature at the end. And I ended up drawing that black for some reason. So let's just change that back to blue, and then we just shade it. Now, and then we just put on the peak value. And there's one other thing that comes out from this diagram. So that's 9 kilonewton meters is the peak load. And it's true always, where the shear crosses the x-axis. So where you've got zero shear, that will be a maximum moment. It might not be the only maximum, so let's come back up here. So we've got a maximum here, shear is 0, or maximum or minimum. Here's a little minimum, it's gone down, got to here, that's 0 shear. Then it's gone back up, what was that? That must have been crossing, yeah, it was crossing a little concentrated moment, a pure moment. But we've got another maximum here, and that was also a 0 shear point. So wherever you've got shear, except at the ends, wherever you've got shear as 0 within the beam itself, then your moment's going to have a local maximum. It's going to be or a minimum. It's going to be a little point or a trough, and the bottom of the trough or the top of the point is going to be at the point where it's got 0 shear. Okay, so this one's got 3. Let's just check the other ones, make sure it's still true. Cantilever doesn't really have any local maximums. It doesn't have any peaks or troughs, so it doesn't work for that one. But it does work for the simple point load. So where have you got maximum moment? Where there's 0 shear, and that's always the case. You'll always get a local maximum or minimum at a point of 0 shear. And just so you're clear on what I mean by a local maximum or a minimum, if you've got some kind of random thing like this, anywhere where it goes from going up to going down is a local maximum or minimum. So it's that one. There's one there, just slightly. This one. There's one here. There's one there. There's one there. There's one there. There's one there. There's another one. It'll be a bit wobbly along the end here, but all those are local maximums or minimums. So if you had a shear diagram like that, at all of those little peaks or troughs, there would be 0 shear at the point where it was either maximum or minimum. Okay. Now we don't want to use the method of sections every time, it's too time consuming. So what we want to look is at these quick rules. It gets a little bit trickier for when you've got a line load. So you've got a line load, you end up with a UDL, constant load per unit length. That leads you to a shear force diagram that looks like this. So it's a straight line, but it's inclined because it's a UDL. And so to get from this to the moment diagram, the easiest rule to follow is that the change in moment is going to be the area under the shear force diagram up to that point. Now you need to know where to start though. So it might be that you have to do a little bit of method of sections just to find a few points. And then in between we can start using this area under the shear force diagram is going to be the change in moment. So let's have a think about that. What we could have done here is we know our starting point because that's a pin, so we know the moment is going to be 0 at that point. Then we can go along 1 meter and we can think, look, what's the area under this shear force diagram up to 1 meter? So just let me highlight that. And so we're looking at the area up to 1 meter. And so this is 6 kilonewtons. This is 4 kilonewtons, must be. 4 kilonewtons at that point. And so the area under there is going to be 4 times 1 plus a half times 2 times 1. So just the area of the rectangle, the area of the triangle. So it's going to be 5 times 1, which is equal to 5. So then we'd know that at 1 meter along, we're going to go 5. Then either we could keep doing that, so we could figure out the area here, like so, and figure out that whole area, and that would give us the next point. Then we could figure out this whole area, could get the next point from that, or we can just look at the next area along here and just think of the change. What's the change between there and there going to be? So if we look at this one here, we've now got, this is going to be at 4, this one's going to be at 2, and so it's going to be 3 times 1, so it's going to change by 3, so we're going to go 5 to negative 8. To positive 8. See, even I have to think about it twice. So to positive 8. And then we can go along to the next one. What's the area under here? We've just got 2 times 1 times a half. So it's just 1. And so then we're going to increase by 1. And all of this is positive. So we're going in the positive direction. Downwards the positive direction. So we're going to go 1 positive. Then we get to the other side. And so we can keep looking at what's going to change. So we'll look at this area next. That's 1 again, but this time it's negative, so we have to go in the negative direction on the moment diagram, which is upwards on a moment diagram. And so it's going to go 1 to here. And similarly, you can see the symmetry coming in. That's the other thing you could do, is you could just say it's symmetrical. And so you can just keep going through and you'll get that graph. Okay, and so you don't even need to use any maths. You can do it all graphically. And I think that'll pretty much always be the case. You'll always be able to do it graphically. Cool. That's that one done. So let's now move on to, I'll maybe do a quick summary of all the different rules for moments, and then we'll just do a couple more examples that are a bit putting all of this stuff together, just doing it all graphically and not going through all this stuff about the method of sections.